That is why the only actor called Rajini is called a superstar. The same way, and he is a common, and he is actually not only the belonging of his own family, he is a common man, and the belonging, he is a belongingness of everybody is living in Tamil Nadu and throughout India. So likewise, when any material starts behaving like a superconductor, and it must have some property. One, the electrical resistivity called rho becomes 0. What happens to this? The conductivity becomes 1 by rho, called reciprocal of the electrical resistivity. So it becomes 1 by 0, becomes infinity. And also third one, the magnetic properties of a superconductor must be completely excluded from it. So I repeat again in wording. Electrical resistivity of a superconductor drops to 0, and the reciprocal of the electrical resistivity is called conductivity, becomes infinity, and magnetic properties are completely excluded from the superconductor materials. The next we will go into another important 5-mark question from the same area called application of the superconductor. But there are many applications are there given in a textbook, and I can say very shortly that what are the things which you feel are not possible, can be possible if more superconductors are actually found. I hope you can able to understand what I am talking. For example, and just one example I will give you. You can easily go through the textbook and you can able to understand what I am trying to say. But now we are launching a satellite with the help of a rocket. But in the future, if many superconductors are found by the young people, what happens? You don't need to spend a huge amount of money for constructing your rocket. You can use your rocket propulsion superconductor magnetic rocket propulsion system can be used in the later years. With that, you can simply launch any satellite from the earth with a less expenditure of money. So similarly, and also I can say now in the field of medicine, so doctors are actually operating. Now the knives are used, and the patient must shed a lot amount of blood. But in the future, using the high gradient magnetic separation method, we can simply operate without shedding the blood, and the diseased cells can simply be removed from the original living normal cells. So what are the things which you don't feel are not possible can be possible if many more superconductors are found in future, and if they are in a different department in different fields, and enormous kind of unimaginary things can be made possible in future. And these are all listed up in applications of the semiconductor. And next we will move on to the next topic called carbon resistor. So normally if you use a wire as a resistance, as I told earlier, any wire will have a resistance. Without a resistance, a conductor or a wire cannot exist. But the resistance of wire is directly proportional to the length of the conductor. The resistance of the wire is directly proportional to the length of the conductor, and inversely proportional to the area of the cross section. So if you have a very lengthy wire, definitely that wire must have a larger resistance. But if you use a wire as a resistance for the electrical circuit or electronic circuit, it is very highly expensive, and you cannot be able to use that huge wire for a smaller circuit which uses a very high resistance. It is quite not possible. But how to actually replace the particular resistance called wire wound resistor? Any wire used as a resistance can otherwise called wire wound resistor. But instead of that, we have got another sophisticated resistance called carbon resistor. What do you mean by a carbon resistor? It's simply a ceramic core, and you can see when you do the practicals in +2, and when you do that operational amplifier, you can use for 22K and 47K, 33K, and these are all different values of resistor. They are all called carbon resistor. So this ceramic core will be there, and on the both ends here wire is actually fixed. Here lead is fixed, and over it a carbon is deposited in the form of crystalline. So carbon crystalline is deposited on the ceramic core, that is called carbon resistor. So you can buy the carbon resistor in different values according to the necessity that you want it. But we are going to discuss about only a 3 color coding resistor in our textbook. And how to, and when you just buy the resistor from the shop, you can see some color coding are actually drawn on the surface of the carbon resistor. On the left hand you can see 3 color coding. On the right extreme you will get only 1 color coding. And these 3 color coding will give you the value of a carbon resistor. And the last color coding will give you a tolerance called percentage of reliability, or a tolerance value of the carbon resistor. And what is the maximum value, what is the minimum range for which you can be able to use this resistor can be explained with the help of this particular last color coding called tolerance color coding. It is otherwise called percentage of reliability. And these 3, for example, how to identify the values based on the color which are drawn, which are marked on the carbon resistor. But you have got a table, BBI, Great Britain, very good wine. You can look at the textbook, you can find out BBI. Look at the first letter of a BBI. BBI, Great Britain, and very good wine. You will get 10 colors. So you have to start the number from 0 to 9. 0 to 9, and look at the BBI. Black, brown and red, then orange, yellow, then blue, violet and grey and white. So when you look at the first letters of all the colors which just now I told, you can be able to say BBI, Great Britain, very good wife. Start the number of those colors right from 0 to 9, you will get 10 colors. And each and every color has got corresponding code right from 0 to 9. And if I draw a color code, so take this as an example. The first color coding is drawn with the yellow, and second color code is drawn with the violet, and third color coding is drawn with the orange color code, and the last one is called with the silver. Now yellow, when you look at the table of BBI Great Britain, yellow has 4 and violet has 7, and this one orange, this is not 0, this is not orange has a value of 3, so into 10 to the power 3, or if you want to express as a power of 10 to the power 3, you can simply add 3 zeros. You can use either of the techniques. And this silver, what is the tolerance color coding for the last color coding? So in the case of silver, then red. So silver or a gold, you can say the color coding resistor are silver, gold, red. Silver, gold and red. This is silver, gold, red and brown are having the tolerance value, namely 10%, so half of it 5%, then 2% and 1% respectively. So this is for silver, this is for a gold, this is for red, and brown has a tolerance color coding value 1%. So the silver has 10%. So the value of this carbon resistor with the yellow, violet, orange with the silver tolerance color coding can be written as 47,000 ohm, and plus or minus the tolerance color coding must be preceded by the plus or minus and 10%. Or if you want to express in terms of K, 47 kilo ohm plus or minus 10%. So it's a very simple formula, simple way in which you can understand the color coding from the table given in the textbook, and with that you just find out which one of the color is for tolerance color coding. You can easily find out the value of the carbon resistor with the tolerance value. Now we will go to the next topic called a combination of resistors. In a simple circuit, several many resistors or in a simple circuit several many resistors are connected either in series or in parallel, for which you can apply the Ohm's law. If the circuit is very simple, you can definitely apply the Ohm's law. So as we have studied in the first chapter, the capacitor in series and parallel, similar to that we are going to study how the capacitors are going to be connected in series or in parallel. For those we can be able to calculate the effective capacitance of the capacitors in series and parallel. First we will see that a resistors in series. So take that 3 resistors. So as shown in the book, we take the 4. So whose resistances are R1, R2, R3 and R4 are connected to the battery as shown in the diagram. The potential of a battery is equally shared by all these resistors across it. So I can say the potential across the resistor, first resistor can be V1 and second one can be V2 and third one can be V3 and fourth one can be V4. And current flowing through all the resistors, since they are in series, are the same. So this will be I and I and I and I. So current flowing through all the resistors will be the same, but potential difference developed across each and every resistor when they are in series will differ. So again I stress that important point that if the resistors are connected in series, the potential difference developed across each and every resistor will differ, but current flowing through the resistor will be the same. Now we can apply the Ohm's law. So what is Ohm's law? How will you express this V in terms of Ohm's law? So V is equal to IR. Since this battery whose potential is used to connect these resistors in series, I can say as RS. Similarly, how to write V1? V1 is equal to I into R1. Similarly, you can say V4 is equal to I into R4. The potential of the battery is divided into different potential across each and every resistor. So V1 plus V2 plus V3 plus V4. What is V? V is equal to I into RS. This is I into R1, I into R2 plus I into R3 plus I into R4. I hope you can able to follow me. Yeah, good. So now take the RS, I into RS. I is common in all the terms. You take it out. So R1 plus R2 plus R3 plus R4. This is not RT, R3. Okay, good. So this is nothing but cancel I. You will get RS is equal to R1 plus R2 plus R3 plus R4. So what is an idea you get it? When the resistors are connected in series, whose effective resistance is numerically equal to the sum of the resistances of the individual resistors. So now we will go into another type of resistors, another combination of resistors when they are in parallel. When the same kind of resistors of different resistances, when they are in parallel, as shown in the diagram, see, first resistances, second resistances, third resistance and fourth resistance. When they are in parallel, and if the entire combination of resistance are connected to the battery as shown in the diagram, the potential developed across each and every resistance, R1, R2, R3 and R4, the potential will be the same and current flowing through each and every resistor will be different. Same concept we have already studied in capacitor. So current flowing the first resistor will be I1, I2, I3 and I4. Now that you can write V is equal to IR according to the Ohm's law for the battery. This battery connects all these four resistances in parallel. You can use the RP, and I is equal to V by RP. So based on that, what is I1? I1 is equal to V by R1. So similarly, what is I4? I4 is equal to V by R4. Now the current of a battery is divided into 4 different currents. So I can write I is equal to I1 plus I2 plus I3 plus I4. Substitute all the values of I, right from I1 to I4 to that particular term. So you can say I is equal to, see, I is equal to V by RP. So V by RP is equal to V by R1 plus V by R2, V by R3 plus V by R4. Take that the V out. So V by RP is equal to V into 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4, and remove the V since it is common in both the terms, in both the left hand side and right hand side. So we can write finally RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4. So now I am going to give a conclusion for the final statement. The reciprocal of the effective resistance of the resistors when they are connected in parallel is numerically equal to the sum of the reciprocal of the resistance of the individual resistors. Next, we will go into another topic called temperature dependence of a resistance. What is the next topic? Can you repeat? The temperature dependence of a resistance. So when you alter the temperature for a conductor, how the resistance is going to change? So when you alter the different value of a temperature for the conductor, the resistance of a conductor goes on changing. How it actually changes? In the case of a conductors, when the temperature increases, the resistance will also increase. But in the case of a semiconductor and the insulators, the case of semiconductor and the insulator, when temperature increases, the resistance decreases. So in the case of semiconductors and increases, in the case of semiconductor and the insulator, when temperature increases and resistance decreases. So now based on that, we can write equations. When you maintain a conductor at a 0 degree temperature, 0 degree Celsius, the corresponding resistance can be referred as R0. R0 means resistance at 0 degree Celsius. And when you increase the temperature for a conductor at one particular higher temperature, what should be the resistance? That can be denoted by a symbol RT. So if you want to relate both the resistances at 0 degree Celsius at some higher temperature, then you have to write the expression RT is equal to R0 of 1 plus alpha T. So this is the relationship one can able to write between the temperature of resistance at a higher temperature and the temperature of resistance at a 0 degree Celsius. But if you want to express what is called alpha, alpha can be written as RT by RT minus R0 by R0 into T. See, this RT minus R0 is the increasing in resistance, and this is the R0 is the resistance at a 0 degree Celsius, and T is the temperature. And what do you mean by alpha? Alpha is temperature coefficient of a resistance of a given material. I repeat, alpha means